We're going to talk about approximate trusses. So why do we need to approximate a truss? Well, we need to approximate a truss if it is indeterminate. Remember our determinacy equation for trusses, which is B plus R and its relationship to 2 times J. I said R and then I wrote a 2. So B is the number of bars. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Please note that in the middle of my X's here, I do not have dots, which means there are not joints there. Reactions is number of reactions, 1, 2, 3. And then 2 times the number of joints, 1, 2, 3, 4, 5, 6. And we end up with 14 and 12. So 14 is definitely greater than 12. So this is indeterminate. And that means we cannot solve this truss by method of joints or method of sections. So we're going to bring in an approximate method. We have 2 approximate methods for this particular truss, and this is all we're going to be dealing with, which is the squares with the X's in the middle. That's our only truss. So we've got 2 different methods. Method number 1 is where the members are slender. So if you can imagine a slender member, it is not going to hold compression very well, but it will hold tension. When we talk about the members are slender, we're talking about the X's in the middle here. So that would be members AE, BD, CE, and BF. And your book does not define a ratio or a certain cross-sectional area size that is slender, but on your homework it tells you whether or not to consider them slender or not slender. So that's all you need to worry about for right now. So if I have this 2-bay truss here, and I have a 100-pound force acting at joint B, I have a pin at D and roller at F, how would I use method 1 to solve for the reactions at joint A, or the forces acting at joint A? The first thing I'm going to do is solve for the reactions at D and F. We've got symmetrically loaded, symmetrically supported, which means dy is going to be 50 pounds, as is Fy. I don't have anything acting in the x direction, so dx will be equal to 0. Next, I'm going to take a section right through this first bay here, and I'm going to take it towards AD. Here's my free body diagram, section 1. If I sum for forces in the y direction, which is the only direction that my angled components act in, right? I've got 4 acting in the x direction, but only 2 in the y direction. I find that I am out of balance by 50. So force AE and force DB, their y components, need to equal 50 down. So if we are assuming this is slender, that means that members acting in compression cannot handle a load, so it's going to be 0. So the entire load is going to go into the member in tension. So the next question is, how do we determine if it's in tension or compression? We need 50 down. So that means AE needs to act down in the y direction and DB needs to act down in the y direction. If I am following the line of action of member AE, it's acting down and to the right. If I'm following the line of action for DB, In order for it to act down, it needs to go to the left. So which one's in compression? Force DB is in compression because it needs to go down and to the left to compensate for that 50 pounds going up. So I put a 0 on force DB because it is a slender member and cannot handle compression. So force AE, the Y direction, is going to take up the entire 50 pounds in the Y direction. Now, I don't think I put distances on here. Nope, surprise. So if I come back here and put distances on that my entire truss is 4.5 feet tall and 6 feet wide, then I can come down here and set up similar triangles. So I have 50 in the Y direction over the X direction of force AE is equal to 4.5 in the Y direction over 6 in the X direction for my lengths. And I find that the X component of my member is 66 2/3 pounds. So my resultant force AE is going to equal 250 squared plus 66.67 squared, square root of the sum of the squares. And I get 83 1/3 pounds tension for force AE. Now that I have that, I can sum moments about D. And I find that force AB is equal to 66.67 pounds in compression. Now this one can be in compression because the only slender members that we're talking about are those crossing members in the middle of the bays, not the entire truss. Okay, so AB can be in compression. And then to finish out solving for joint A, I need a joint A free body diagram. And I can sum for forces in the Y direction and get force AD. Force AD also equals 50 pounds in compression. And again, it can handle compression because the only slender members are the X's. For method 2, we assume the members are not slender, which means they can handle both tension and compression. So this time I'm given a 3-bay truss, and I gave you the length this time, 2 meters by 2 meters. I have 3 loads, 40 newtons at A, 10 newtons at D, 15 newtons at E, and I want to find the forces in members CF, DE, and CE. So using method of sections, I'm going to go ahead and cut right through here, and I'm going to take my section up so I do not have to mess with the reactions at G and H. My free body diagram, section 1, if I sum for forces in the X direction, which again is where my diagonals are concerned, I have 40 newtons minus 10 newtons, and that needs to be what force CF in the X direction and force DE in the X direction equal. So we've got 30 newtons to the left to compensate for the 30 newtons that were off to the right for our loads. So coming in here, I'm going to put to the left for CF and to the left for DE. Okay, again, following the line of action, in order for CF to go left, it needs to go up and to the left. And for DE to go left in the horizontal component, it needs to go down and to the left. Okay, following those line of actions. To force member, I have to follow the line of action between the two locations of the forces. So for CF, I have to follow line CF, and for DE, I have to follow line DE. This time we're using method 2, which means that each member can take on some load. So how do we decide how much? We're just going to split it equally. So I've got 15 newtons here horizontally and 15 newtons here horizontally. The way I have my truss drawn, I have 2 meters wide and 2 meters tall. So that means that my angles are going to be 15 left and 15 up for CF and 15 down for DE. I'm sorry, this looks really crowded. I apologize. So that means that force CF is equal to 15 square roots of 2 newtons in compression, and force DE is equal to 15 square roots of 2 newtons in tension. Again, it can handle both because they are not slender members and can handle tension and compression. The last one that I wanted was force CE, and I'm going to solve that by summing moments about D. Summing moments about D, I have force CE, the Y component of force CF, and then my horizontal load up at A of 40. And I find that force CE is equal to a positive 55 newtons, which means in tension, because I assumed CE in tension, got a positive answer. There it is.